Hello everyone, I'm Kamal Ndous, and on behalf of my co-authors Douglas Eck, Sergey Levine, and Natasha Jakes, I'm excited to present this work called Learning Social Learning. This work is motivated by the importance of social learning to human cognitive capabilities. As humans, we can develop skills by learning from experts, for example, with verbal or written instructions, with formal schooling, or with pure mimicry. We're able to learn from each other without direct access to the experiences or memories of other humans. With humans, all teaching and learning is mediated by the environment. The sophistication and variety of the behaviors that modern humans engage in demonstrates the power of this learning paradigm. For instance, we can read and write books, administer space programs, debug cloud computing infrastructure, rollerblade, and participate in geopolitics. And of course, it would be very unlikely for solitary humans to develop the skills necessary for these tasks in isolation. Social learning could help AI agents learn faster, explore safely, and adapt more rapidly to new environments. For instance, person-following robots can avoid areas that are unsafe for pedestrians by taking navigational cues from humans who already know how to avoid areas where they might get hit by cars. Even relatively low-risk, mundane tasks like unloading a dishwasher pose a significant robotics challenge due to the variety of specific dishwasher configurations. A household robot with a human-like capacity for social learning could learn how to unload a particular dishwasher by observing a human demonstrate that task. In these examples, the human experts do not generate trajectories or policies that the robots could directly use for imitation learning. With that in mind, this work focuses on social reinforcement learning among independent agents in multi-agent RL environments. Multiple independent agents interact in a shared environment, but both training and execution are decentralized. In our case, each agent is trained with recurrent PPO. We also focus on scenarios without strategic interactions, where agents' rewards do not explicitly depend on the rewards obtained by other agents. In this paper, we introduce a novel sparse reward hard exploration grid world environment called Goal Cycle. Goal Cycle heavily penalizes individual exploration, and this penalty encourages novices to develop social policies that instead rely on cues from expert agents. But even with an environment designed to facilitate social learning, we find that agents fail to perform well when trained with standard model-free reinforcement learning. We track down the source of this issue and show that adding an auxiliary unsupervised prediction loss helps agents learn to use social cues to solve sparse reward tasks. We refer to this treatment, social learning with an auxiliary prediction loss, as sociable. Okay, this is all well and good, but in a sense, we just solved the task that we made up. What good is that? Well, we find that the learned social policies are quite robust. Sociable agents can make use of cues from experts in zero-shot transfer tasks to outperform solitary learners. Put another way, social training in Goal Cycle allows us to obtain generalized social learning policies that are helpful for various expert-guided grid world navigation tasks. This is an example of a Goal Cycle environment. During each episode, 3 goal tiles and some obstructions are placed randomly. Agents receive sparse rewards when they traverse the goals in a certain order, and penalties whenever they make a mistake. Agent observations consist of egocentric RGB images of the tiles in their vicinity, and they observe themselves in their own partial views, as well as any other agents that happen to be nearby. In Goal Cycle, the color of each agent changes from red to blue as it accumulates rewards during an episode. If an agent incurs a penalty by navigating to a goal tile out of order, then its color resets to red. The goals themselves are visually indistinguishable, so it's only by observing their own color that agents are able to determine whether they're traversing the goals in the correct order. The prestige coloring also helps signal the skill of each agent to other agents in the environment. During each episode, expert agents are able to locate the goals, quickly determine the correct goal traversal order, and then cycle between them, accumulating rewards until the end of the episode. In the example shown here, the agent makes a couple mistakes near the beginning of the episode, but quickly identifies the correct cycle, then exploits it for the remainder of the episode. Since the correct traversal order can only be identified through trial and error, even expert agents sometimes incur penalties while determining it. When the mistake penalty is large, novice agents learning from scratch are unable to learn effective policies. As this clip shows, such agents learn to find and navigate to a first goal since the first goal encountered in an episode always gives a reward. But then they avoid all goal tiles for the remainder of the episode. This is where expert cues could come in handy. Novices could just follow the path shown by the experts to collect rewards without themselves risking penalties. However, we find that with vanilla PPO, novice agents trained in the presence of experts are no more effective than those trained alone. Although the expert agents identify and incidentally demonstrate the correct goal traversal order during each episode, novices trained with vanilla model-free reinforcement learning fail to make use of that information. To see why that might be the case, consider a social door key environment. The blue agent is an expert and the red agent is a novice. Since it's a hard exploration task, let's suppose the novice red agent receives no rewards during this particular episode. The transition from S to S tilde shows the red agent that transitions from closed doors to open doors are possible in the environment, and we'd like the red agent to use this information. In the context of deep reinforcement learning, this would mean updating its representations to account for this possibility. This equation shows the gradient used to update policy parameters for a Monte Carlo policy gradient. Since the novice doesn't receive rewards in the episode, the contribution to the gradient from the potentially valuable demonstration vanishes, and the demonstration is ultimately uninformative. And we observe a similar problem in tabular Q learning. As the novice collects experience without receiving rewards, the TD targets for all visited states, including those that contain valuable demonstrations, are pushed towards 0. So absent a reward, the novice isn't able to learn anything useful. To help with this problem, we propose augmenting the neural network architecture we use for model-free reinforcement learning with an auxiliary prediction task. Our base actor-critic architecture has input layers and an LSTM layer shared between the policy and value functions. Our auxiliary prediction task involves predicting the next observation in each state, conditional on any possible action. This is implemented as a sequence of deconvolution layers mirroring the input convolutions. We use PPO with generalized advantage estimation to train the policy and value heads. During parameter updates, the L1 error between the observed and predicted pixels is used to update the auxiliary layers as well as the shared input and LSTM layers. This auxiliary prediction loss allows the representations in the shared layers to improve, even when the reward signal itself is uninformative. These images show the predicted next observations for a near-expert agent whose current observation is shown on the left of the dotted line. Portions of the agent's view that are obstructed by the brown obstacle tiles are shown in purple. The agent has a discrete policy, and its possible actions include move forward, rotate left, rotate right, and do nothing. We can see that the predicted observations, conditional on the movement actions, are reasonably accurate. The agent can predict what the world will look like when it rotates, and it has learned some of the visual obstruction logic. Interestingly, its prediction conditional on doing nothing is of the poorest quality, even though it seems like that would be the easiest prediction to make. This is probably because goal cycle experts are usually in motion, so the auxiliary predictions conditional on staying still just don't get much training data. With this auxiliary loss, novices trained from scratch in the presence of experts are able to learn effective policies. 4 out of the 5 seeds we trained with Social were able to outperform solitary novices, and in fact each of these 4 actually outperformed the experts with which they shared an environment. The individual seeds are shown in the dotted green lines. Agents were only able to learn effective policies when trained with both the auxiliary loss and in the presence of experts. That is, 0 of 5 seeds succeeded when trained with vanilla PPO in the presence of experts, and 0 out of 5 seeds succeeded when trained with the auxiliary loss but without the experts. In another ablation, we replaced the prediction task with an input reconstruction task. Agents were trained to reconstruct their current observations rather than predicting the next one. With this auxiliary reconstruction loss, 3 out of the 5 agents learned to outperform solitary novices, and the individual seeds are shown in the dotted orange lines. This clip demonstrates the behavior of a Social agent with a converged social policy. The social learner's partial view is highlighted in red, and its observations are shown at the top of the column on the right. The social agent immediately finds a goal and sits in front of it, waiting for an expert to turn up. When such an expert appears, the social learner follows it for the rest of the episode. This shows why the social policies are able to attain higher rewards than the experts. While the experts sometimes incur penalties while establishing the correct goal traversal order, the social learners avoid these penalties by following the experts after they've identified it. So we just saw that social agents trained with experts in goal cycle are able to learn policies that benefit from the presence of those experts, and notably that outperform solitary agents. We tested the generality of those learned social policies by measuring the zero-shot performance of those social learners in 2 transfer tasks. First, a 4-goal variant of the goal cycle task, shown on the left, and also a much larger 4-room maze, shown on the right. And as you can see, in both cases, the social policies transfer reasonably well. These charts compare the zero-shot transfer performance of 3 groups of agents from goal cycle: the sociable agents, the experts from which they learned, and the solitary novices that learned avoidant policies. In both transfer environments, the social learners easily outperformed their experts as well as the solo learners. The 3 goal cycle experts that didn't use social policies notably performed terribly at the 4-goal variant of that task. The individual exploration policies do not generalize well. Note that these tasks show the best 3 of 5 seeds in order to emphasize the performance of the converged social policies. So far in this discussion, I've been referring to agents that can individually solve the goal cycle task as experts. And when I say the sociable agents learn from the experts, I'm kind of implying that they learn to do what the experts do. But of course, the experts and the social learners are doing 2 very different things. The experts have learned to identify the goal traversal order, but the video suggests that the social learners converge on policies that are more like follow the blue agent. And indeed, we find that if we put the converged social learners in solitary goal cycle environments, they just wait around forever for experts that never show up. Empirically, we observe that early in training, the social learners do have some individual goal cycle skill, but this diminishes as they learn to rely more heavily on cues from the expert agents. And this chart shows this happening to a single sociable seed. The orange line shows the solitary skill peaking after about 300,000 episodes, then diminishing completely. However, we found that if we train them on a mixture of social and solitary environments, sociable agents were able to learn the generalized social learning policies we discussed earlier, and also to perform well at the solitary 3-goal task. We took a checkpoint of the same agent before its solitary skill collapsed completely, and continued training it with such a mixture. Its solitary 3-goal skill continued to improve, as shown by the dashed orange line. But also its social learning policy continued to improve, as shown by the dashed purple line. So, just to recap, the high penalty goal cycle environments are hard enough that we didn't observe a single solitary agent being able to learn an effective policy. Our experts were trained with a curriculum in lower penalty variants. But what we see here is that just training with skilled agents some fraction of the time was enough to get sociable agents to learn this challenging individual skill. So in summary, we found that model-free RL agents struggle with social learning in sparse reward contexts. We examined this issue analytically and empirically, and find that an auxiliary prediction loss helps agents learn social policies. Using social learning with an auxiliary prediction loss, or sociable, agents were able to learn robust social policies that allowed them to develop skills which would otherwise be inaccessible. These social policies are versatile and give them better zero-shot generalization capabilities than solitary learners in other guided exploratory navigation tasks. There are many interesting directions for future work. In our paper, we show that social learning can still occur when novices learn from imperfect experts, but we don't consider scenarios where experts in a single learning environment have varying degrees of expertise. Identifying relevant experts is an important aspect of social learning in humans and animals, so we could ask whether that faculty emerges on its own, and if not, how to foster it. Social learning also holds lots of promise for real-world applications like robotics, and to fulfill that promise, it'll be necessary to leave our simple grid worlds. Finally, in this work we made an effort to avoid strategic interactions between agents, and we've left open the question of whether novices could learn faster if the experts were rewarded for effective teaching.